when doing integration by parts, so the process is, here's the integration by parts formula. You start by finding u, du, v, and dv. So you have the integral that you're trying to solve, and you choose which part of that integral is going to be u and which part is going to be dv. That's how you start. Then you differentiate u to get du, and you integrate dv to get v. And when you integrate dv, it's common practice that you omit the arbitrary constant at that step. And when we went through the textbook and talked about this, I mentioned that the reason we omit the constant is because if we included it, it would just in the end get absorbed into that final constant. And that is true in one sense, but that's not the full story. So I wanted to go ahead and make this video to explain what this is all about. Okay, so to illustrate this, let's solve this integral here. And I chose this integral because to solve this, we'll have to do integration by parts 3 times. So you'll get the full picture of why we omit that constant with this problem. So, okay, let's choose what's going to be u and what's going to be dv. E to the z is easy to both integrate and differentiate. Z cubed is easy to both integrate and differentiate, but if we had a choice, we'd rather differentiate. So we'll say that u is equal to z cubed and dv is equal to e to the z dz. All right, so du is equal to 3z squared dz, and now here we integrate both sides and we get v is equal to e to the z, and we're going to put plus c1. I just want to point out that, in general, this is the correct integral. Okay, in any other situation, you always want to put that arbitrary constant. Like if there's a situation where you're not putting the arbitrary constant, then you want to identify, you want to make sure you understand why you're not putting that constant. There's got to be a special reason. Otherwise, it's not correct. So in a general situation, if we didn't do this, put this constant, it's not like this is wrong, but we're going to be missing solutions. Okay, so for any situation, I'm going to say this again, any situation where you're doing an integration and you're not putting the arbitrary constant, remember that's not correct, and you want to make sure you clearly understand why you're not putting it. Okay, so now let's construct the formula. So we've got z cubed e to the z dz is equal to u times v minus the integral of v du. So let's bring out the 3. Okay, so we've got z cubed e to the z plus c1 z cubed minus, okay, so what I'm going to do is we'll do, this is 3, if we separate this integral here, we will have minus 3c1, the integral of z squared dz, and then minus 3 integral of z squared e to the z dz. Right? You see how that's correct there? You can separate this into the integral of z squared e to the z dz plus the integral of c1 z squared dz. And then you distribute the minus 3 and you get this. Okay, so we've got z squared e to the z plus c1z cubed minus 3c1, and now here doing this integral, we've got 1/3 z cubed, and then plus another constant, minus, then we'll just come back to this. All right. So we've got minus c1z cubed minus 3c1c2 Okay. So what I didn't mention in the video where we went to the textbook, all I talked about was that this constant here kind of ends up getting absorbed into the final constant. That is true. But another thing that happens is you get something like this cancels out, right? C1z cubed minus C1z cubed. That's another important consequence of the way this equation works. And so in a more typical integration by parts problem, we get to this step here. So let's write this out. Z squared e to the z, and I'll do this. Take that back. Minus 3c1 c2. So in a typical integration by parts problem, when we get to this step, this integral, we can just go ahead and solve it. And we solve it, and we get some function of z, another constant, and then this constant plus or minus that constant, you just turn into one arbitrary constant, right? This 3c1c2 is just a constant. And then when you add or subtract that from whatever constant comes out of here, that's just, you just end up putting c in the end. So you get some function of z, and then here's another function with the z in it, and then the constant, and then you're done. So yes, like this, it kind of like this constant ends up getting absorbed into the final constant, into one, and with the rest of the problem. But I didn't mention it's also this canceling here that takes place. Okay, now, but for this problem, we have to do integration by parts again. So it's going to just, the same exact thing is going to continue to happen. We're going to do integration by parts again. We're going to get a canceling, and it'll be the same thing happening. But I thought, let me go ahead and illustrate how this all comes together. So, all right. I'm going to say u is equal to z squared. dv is equal to e to the z dz. So du is equal to 2z dz. V is equal to e to the z, and then let's see, how will we do this? Yeah, this might get a little complicated, but let me just try and save all of the constants so we can get the full picture of this. It'll be interesting. C3. Okay, so the integral of z squared e to the z dz is equal to u times v minus the integral of v du. So let's take out this 2. Okay, so what we have is, we'll have minus 2c integral of z dz. Okay. Minus 2c3. And then minus 2 integral of z e to the z dz. Okay. Here we've got z e to the z plus c3, z squared e to the z plus c3z squared. Okay. then here we get 2c3, and then, all right, so 2c minus 2c3, and then we get 1/2 z squared plus c4. That was the integral of z dz, right? So, okay, we've got z squared e to the z plus c3 z squared minus c3 z squared minus 2c3 c4 minus, okay, so there you go. You see, those cancel. So there we go. So now let's put this in here. So z squared e to the z minus 2c3 c4 minus 2 okay. Okay, so we've got z squared e to the z minus 3c1 c2 minus 3z squared e to the z minus 6 c3 c4 minus 6 z e to the z, integral z e to the z dz. Okay, so z squared e to the z minus 3z squared e to the z is minus 2z squared e to the z minus 3c1 c2 minus 6 c3 c4 minus 6 integral of z e to the z dz. All right, now we need to use integration by parts again. So, okay, u is equal to z, dv is equal to e to the z, dz, du is equal to dz, v is equal to e to the z plus, what are we on now? C5. Okay, so the integral of z e to the z dz is equal to u times v minus the integral of v du. Okay, so we've got minus the integral of C5. Okay, let's minus C5 integral dz minus integral of e to the z dz. Okay, so we've got, and this is going to be c or z plus c6. Okay, so this is going to be minus c5z minus c5c6. Okay, and then this is going to be e to the z plus c7. Okay, then this is z e to the z plus c5z. Okay, and there you go. You see, those cancel, and we're left with z e to the z minus c5 c6 minus e to the z minus c7. So replacing this. Z e to the z minus e to the z minus c5 c6 minus c7. Okay. So minus 2z squared e to the z minus 3c1 c2 minus 6c3 c4 minus 6z e to the z plus 6 e to the z plus 6c5 c6 plus 6c7. All right. Okay, for some reason, I turned this into a z squared, which is incorrect. So this is z cubed. This is z cubed. This is z cubed. So then I shouldn't have combined these two. So what we have is here, this should be, so we have the z cubed e to the z, and then minus 3z squared e to the z, like that. Okay. Same here. Okay, so we've got z cubed e to the z minus 3z squared e to the z minus 6z e to the z plus 6 e to the z, and then minus 3c1 c2 minus 6c3 c4 plus 6c5 c6 plus 6c7. All right, and so what is this? This is just an arbitrary constant, right? These are all constants. If we were left with one of our constants, c1, c2, c7, with an x or with a z term on it, then that would be an issue. But because these cancel out like this, what happens in the end is all the constants that if we would have carried over all the constants, they would all get absorbed together into one constant. So we could just change this to plus c. Okay, so that's the idea, and so that's why we don't, for the case of integration by parts. If you're doing integration by parts, and you're identifying what u and dv is, and then you integrate to get the v. That's why you don't have to include the arbitrary constant, because of this canceling out here, and because of they all get absorbed together. Well, I erased it, but okay. Now, when I check this integral, this should be a plus, and then this should be a minus. So I'm not sure where exactly the error came in, but this is more about, this video is about showing you why we don't include the constant. So you can go through this and see where the mistake was made, but I think you can agree, though, regardless of this mistake, this mistake here has nothing to do with illustrating how, for integration by parts, why we don't have to include that constant. And again, this is really important that, in general, anytime you integrate like this, I mean, really, anytime you're finding an antiderivative, you include the arbitrary constant. That's the correct answer. And so, if there's a situation where you're not including the arbitrary constant, you want to make sure that you pause and say, okay, do I understand exactly why I'm not including this? And then when you know that you understand, then move forward. It's the same thing with definite integration. You find the antiderivative, but you don't include the arbitrary constant. And so, we talked about that when going over the fundamental theorem, but I think I'm going to make another video doing a definite integral where we include the arbitrary constant and just see what happens.